Hello, welcome back. In this video, we solved problem 15.3.026 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to evaluate this line integral of a vector field over a curve C for several different paths C. We actually have 4 paths. This one is C1, this one is labeled C2, this is labeled C3, and then the 4th one is labeled C4. And then we've got a hint. We're told that if f is conservative, the integration may be easier over an alternate path. And then we're given this line integral. Now, this is called the differential form of the line integral. It's going to help us identify our field f. So let me write that down. Differential form looks like this. The line integral over C of m dx plus n dy. That is equal to the line integral over C of f dotted with dr, where f is a field with components m and n. So when I see this differential form, what I'm thinking of is my field. I'm thinking this function in front of the dx is the x component of my field. We call that m of x and y. And the function in front of the dy is the y component of my field. That negative would be included. We're calling that n of x and y. So let me write that down for this particular problem. Our field is 2x minus 7y plus 1 times I hat plus, actually I'll use not component form, but I'll write it in terms of our standard unit vectors, plus this function times j hat, and I'll distribute that negative as well. So I have negative 7x minus y plus 9 times j hat. Now to give me just a little bit more space, I'll write that down here. And I will write it in component form because that's my preference. My x component is 2x minus 7y plus 1, and my y component, my n, is negative 7x minus y plus 9. Okay, now they mentioned that if f is conservative, the integration may be easier on an alternate path. And in order to make use of that, we need to know a couple of things. We need to know about the fundamental theorem of line integrals and the implications of the fundamental theorem of line integrals. So here is our fundamental theorem of line integrals. This is from the Larson text. It says, let C be a piecewise smooth curve. So we want a curve that's smooth in pieces, lying in an open region R. Now, if f is a field in the plane with component functions m of x and y and n of x and y, and f is conservative, and the component functions m and n are continuous on that open region R that contains our path C, then the line integral over C of our field is equal to the line integral of the gradient of little f, where little f is the potential function for big F. And the only thing we have to do to evaluate that is find that potential function, evaluate it at the end point, and evaluate it at the start point of our path, and subtract. This is very similar to the fundamental theorem of calculus, one version of the fundamental theorem of calculus that you learned in Calculus 1. So there are a few conditions in there. I just want to point them out. First, C has to be piecewise smooth in an open region R. If you're saying to yourself, well, aren't they all in open regions? That open region R is sort of determined by the region of continuity of the component functions of our field F. So if this is our field and that field is conservative, that's a really important part. That's usually the part everyone remembers. And M and N are continuous on that region that contains that piecewise smooth curve C, then this is true. Now that actually gives us a lot more than just this one way of evaluating this line integral. So there are lots of implications for this. First, it says that if C is piecewise smooth in an open region where the component functions of f are continuous, then this line integral is what we call path independent. It really doesn't matter how I get from the start point to the end point. if this is where I'm starting and this is where I'm ending up, if all of the conditions of the theorem are met, so we're talking about a piecewise smooth curve and the component functions of f are continuous and f is conservative, if all of that is true, I can evaluate the line integral over this path, if that's my curve C, or I can take an alternate path. I don't have to take that path because this says it doesn't matter what path you take. The value of the line integral just depends on the value of the potential function at the ending point and the starting point, and we just take their difference. So I could take the path that I'm given, or I could create an alternate path. Maybe I would take the straight line path. That's usually a good choice. Or I might say, you know, I don't want to take that straight line path. Maybe I want to find the potential function and evaluate it at the ending point and starting point and use that to evaluate the integral. So you've got lots of options, but it turns out if all of these conditions are satisfied, you don't have to integrate over that path. You could integrate over pretty much any path you want, as long as you draw a path in a region where the component functions of f are continuous. And I didn't write that here in the implications, but of course, the most important condition is that f is a conservative field. Okay, so let me write down our options. If f is conservative and C is piecewise continuous in an open region where the component functions of f are continuous, you could evaluate the line integral as given. That's one option. So they gave us a path, they gave us 4 paths, and we could parameterize those paths, find the piecewise smooth parameterization, and then evaluate the line integral over that path for C1, C2, C3, and C4. That's a possibility. Or we could say, I don't like that path. I want to take a simpler path. Rather than taking this windy path or this windy path over here, I'm just going to take a simpler path from there to there. Usually the simplest path is just a straight line from one place, from that starting point to that ending point. Now, as long as you start and you end at the same place, that line integral over the simpler path is going to be equal to the line integral over the path that they gave you. And then the third option is you could just find the potential function. You want to find that function f of x and y such that the gradient of little f is equal to big F. Once you do that, if you can identify the starting point and ending point, then you know that the line integral is equal to f at that ending point minus f at that starting point. Now, another implication is that if the curve is closed, so let's say we start here, and then all kinds of funny things happen, and then we end back here, but that's our curve. If our starting point and our ending point are the same, and our curve is piecewise smooth in an open region where the continuous or the component functions of f are continuous and f is conservative, if all of those things are true and we start and we end in the same place, well, then the potential function at that location is going to be the same no matter what. So f at the end point and f at the starting point are the same, and then you end up subtracting them and you will get 0. So we'll say provided all 3 of our conditions hold, the line integral over a closed curve, usually we denote it that way. Little circle just means that the curve is closed. That's just going to be 0. So when I look at this problem and they give me this line integral, which implies that this is my field, and then they give me these 4 paths. I'm hoping that f is conservative, because if f is conservative for this closed loop, I'm going to get 0 from my line integral. And for this closed curve, I'm going to get 0 for my line integral. But of course, I need to check all the fine print. I need to make sure every condition is satisfied before I go ahead and say that those line integrals would be equal to 0. So let's see if our field f is conservative. Now this was our field, remember, in component form. And we've got a test for conservative fields. We actually have a couple of tests. We have one in R2 and then one in R3. Here's the test for conservative fields in R2. So the test for conservative fields in the plane is just this. If f has component functions m and n, and the partial derivative of the x component with respect to y is equal to the partial derivative of the y component with respect to x, then f is conservative. And if f is conservative, that means we can use the fundamental theorem of line integrals or any of these options to evaluate our line integral. And if we're dealing with a closed curve, we can take advantage of the fact that line integral over a closed curve would be 0, provided all of the conditions hold. Okay, so that's the test that we'll use. Let's see if this particular field is conservative. We're hoping it is, because that would make our lives a lot easier. Now remember, this is our m, and this is our n. That's how we're labeling our x and y components respectively. And remember where we got those from up here. We had our line integral in differential form. The function multiplying dx is your m. The function multiplying your dy is your n, or your y component of your field. Now for this problem, I need to determine whether my field is conservative. So I want the partial derivative, the partial derivative of m with respect to y. Well, that doesn't have any y's in it, so I'll get 0. That doesn't have any y's in it, so I'll get 0. But the derivative of a constant times y with respect to y is just the constant. So we get -7. Then I would do the same thing with the y component, but I want to take its derivative with respect to x, treating the other variables as constants. So I look at this, the derivative of a constant times x is just our constant. This doesn't have any x's in it. We're treating y as a constant, so the derivative of that is 0. The derivative of that is 0. So these two partial derivatives are both -7. They're the same. So that means our field is conservative. And that's nice. That means we've got all kinds of options for parts A, B, C, and D. Okay, let's do the easy ones first. For these two, I believe the line integral will be 0, but let's check the conditions of our theorem. First, C has to be piecewise smooth in some open region, and C is piecewise smooth. I've got a smooth piece and a smooth piece and a smooth piece. And here I've got a smooth piece and a smooth piece. So for both of those paths, they're bounded by, or that region that is on the interior there, it's bounded by piecewise smooth curve. And that is lying in the XY plane. So that could be our open region R. We'll think more about that as we look at this third condition. Now we say that the rest of the theorem says that if F is a field with components m and n, and it's conservative, and we've already checked that it is, and the component functions m and n are continuous in R, then this holds and all of this holds. So we just have to look at the component functions of F. Well, the component functions of F are m and n, and they're both just polynomials in x and y. And if they're polynomials in x and y, they're going to be continuous all the time. It does not matter what x or y is. This is continuous in the entire xy plane. So is this. So that piecewise smooth curve is lying in the entire xy plane, where our component functions are continuous, and our field is conservative. So we get all of the conclusions of the fundamental theorem of line integrals, as well as all the implications of that fundamental theorem of line integrals, which includes this implication. Since our curve is piecewise smooth in a region where our component functions are continuous and f is conservative, the line integral over a closed path is going to be 0. So for A, we have the line integral over C1. That's 0 because it's a closed path. You could pick any point to be your starting point and your ending point. I could use x equals 4, y equals 1. This would be the potential function, which we don't know at this point, evaluated at 4, 1, minus the potential function at 4, 1. I don't know what that value is, but I know it's the same thing twice because I'm starting and ending at the same place. So this is going to be 0. And the same thing is true over here. You can pick any point as your starting and ending point. Since we're going in a loop, it's a closed curve. And that line integral is 0. So we get to put a little circle around that integral sign to indicate that that curve is closed. Now for these two guys, you've got options. Again, we could just evaluate the line integral over this path and find our answer. We could find a piecewise smooth parameterization of C2 and just evaluate that. It's not too bad. It's just part of a circle. We could do that with sine and cosine functions pretty easily. That's one option. And then another option is to evaluate the line integral over a simpler path. Since our line integral is path independent, we don't have to stick with the path that they gave us. We can really take a line integral along any path we want, as long as we start at the same place and end at the same place. So I would recommend not taking this little circular arc from this point to this point. Just take the straight line path from x equals 0, y equals -3 to x equals 0, y equals 3. That path is much simpler, and I would integrate over that instead. Now, the third option is to find the potential function of f and then evaluate f at the ending point and starting point and subtracting. That's what we could do if we wanted to. But I think the integration over this simple little path, it's going to be so simple that it's not even worth finding the potential function at this point. So I would recommend for B, just evaluating the line integral over that path instead. So let's do that. Let's set it up. I've got a path from x equals 0, y equals -3 to x equals 0, y equals 3. So I'm starting and ending at the same points that I was starting and ending at before. The line integral over C2 of our field will be equal to the line integral over this path. I'll just call that C2 star, just to give it a name. And remember how we evaluate any line integral. We always write everything in terms of t. Since we're in the plane, I'll want my field in terms of t. When I'm on this path, x would be given by x of t, and y would be given by y of t. We could come up with some piecewise smooth parameterization with component functions x of t and y of t. We will evaluate f at x of t and y of t to write our field entirely in terms of t. And then this dr, well, that's a little displacement piece. You can think of it that way. The displacement is just the velocity times time. So we can do that. And then we'll integrate from one t value to another. We usually let t range from a to b. Those are our choice of variables there. So that's a good plan. But in order to do that, we need to come up with a piecewise smooth parameterization of this little line segment. Now, this line segment is relatively simple. It's on the y-axis. Good night. If we're on the y-axis, our x value is 0. So I can substitute that in pretty simply. Now, the whole time, all we're doing when we're traveling along this path is we're just letting y increase. Y starts at -3 and it goes to 3 and it just increases. So one parameterization, and probably the simplest parameterization I could think of, is just y equals t. That'll be fine. That'll trace out that path as long as we start at t equals -3, so that when t equals -3, y equals -3, and we're there. And then we'll let t run from -3 to 3 to trace out that entire line segment. And that's really nice, very nice and easy. So we will end up evaluating this line integral in this way. We're going to evaluate from this t value to this t value. So our a is -3, our b is 3. We're going to need our field in terms of t. We can find that by letting x equal 0 and letting y equal t, and just substituting into the equation of our field. And we'll take that and we'll dot that with the velocity vector associated with this position vector if we're thinking of some particle traveling along that path. Or you can just think of it as a tangent vector if you want to think geometrically. We'll take that dot product. That's going to give us a function of t. Then we'll integrate that function of t from -3 to 3, and that will give us the answer that we're looking for. It's not too bad at all. We just need to do a little bit more work. Okay, so at this point, we chose an alternate path. And this is just one of many ways that you can solve part B. Oops, from 0, -3 to 0, 3. And then we found a piecewise smooth parameterization of that. And then we know that we can evaluate our line integral over this alternate path using this. It's the same method of evaluation that we use for every line integral. We're just going to use the simple path rather than that semicircle that we were given initially. And that's totally legal because of for a number of reasons, but mostly because f is conservative and has continuous component functions and all that. Okay, and then to go on from here, we just need to find f in terms of t and then r prime and compute the dot product. So let's do that next. Now our field was this. It had components 2x minus 7y plus 1 and -7x minus y plus 9. If I want that in terms of t, I'll replace x with 0 and y with t, because that's what x is equal to when we're on this path. And that's what y can be equal to when I'm on that path, as long as t ranges from -3 to 3. We'll trace out that little path c sub 2 star. So I will evaluate my field at those functions of t, replacing x with 0 and replacing y with t. Easy enough. Get a 0 there and a 0 there and a t there and a t there. So we end up with -7t plus 1 as our x component and -t plus 9 as our y component. So that's our field in terms of t. And once you find that field in terms of t, you want to compute r prime. I almost hesitate to write it down because it's so simple. If r of t is a vector with components 0 and t, r prime is easy enough to find. You just take the derivative component by component. Derivative of 0 is 0. Derivative of t is 1. We're going to take the dot product of that with f to get our integrand there. Now I know our steps are sort of all over the place. This was our first step. The second step was to find that piecewise smooth parameterization. Then we found f in terms of t. Now we're computing r prime. When I look at this, I love this because it tells me exactly what to do. It says find f in terms of t, find r prime. Then the next thing it tells me to do is take the dot product of those guys. So I'll dot f with r prime. So I've got f, which is this function, and I'm dotting that with this function. It's very easy to do. You just take the x component and multiply it by the x component. And then remember, with a dot product, you add. The result of a dot product is always a scalar. Take the y component, so I'll just write in this other order, 9 minus t, and multiply it by the y component. Oops, the derivative of r had component 0 and 1, not 0 and t. Anything times 0 is 0, so that's gone. We just end up with 9 minus t. That's going to be our integrand. That's what gets substituted right there. So from here, we will set up the integral in terms of t. And we'll evaluate it to find the line integral over that path. So the line integral over C2 which remember was the line integral over that path, is equal to the line integral over this alternate path, which I'm calling C2 star. Because all of the conditions of the fundamental theorem of line integrals are met. And so I'll evaluate this integral and it'll be equal to this integral. And this integral is equal to this. So it's the integral from -3 to 3 of f dotted with r prime, which is 9 minus t in terms of t. And we'll just evaluate that integral with respect to t. It's very easy. The antiderivative of a constant with respect to t is a constant times t. Here we'll use the power rule, bring your negative down. Then you want to add 1 to the exponent, divide by the new exponent, then evaluate from t equals -3 to t equals 3. So you just plug in 3, plug in -3, and subtract. Easy breezy. So here I've got 27 minus 9 over 2 minus -27 minus 9 over 2. So I end up with 27 minus 9 over 2. And then we're subtracting, so we can change those signs. Distribute the negative. This reduces with this, and the answer is 54. So the line integral over C2 is 54. And we would have obtained exactly the same answer if we evaluated that line integral over that path by parameterizing that path instead of this one. Instead, we chose to do that line integral instead. Now, the third option, which we didn't take advantage of in this case, is we could have done this. We could have found the potential function and evaluated it at the end point and the start point and subtracted. And that works too. Okay, so that was B. The line integral over C2 of f dotted with dr is 54. So we took care of A, it's a closed path, so we got 0. D was a closed path, so we got 0 for this one. B was not a closed path, but we could take an alternate path, so we took the simpler alternate path. Now, over here, we're in the same situation. We could evaluate the line integral over this path, and this path is given by y equals e to the x. That was given on WebAssign. You could evaluate that if you wanted to, but you don't have to. You can evaluate this line integral instead. You can evaluate the line integral over that path, that simple line segment path, from our starting point to our ending point. That's an option. So you could do that if you want to, but I think I would like to show you an example of how we find the potential function and then evaluate it at the ending point and the starting point. So I think I'm going to do that instead. But know that if you wanted to, rather than integrating over the path given by y equals e to the x from here to here, we could choose to evaluate the line integral from there to there, over the path from there to there instead. It's just up to you. You sort of choose what you'd like to do. And this time I think I would like to find the potential function for f. Okay, so we know already that our field f is conservative, and f had this equation. Let me look it up. It was 2x minus 7y plus 1 times I hat plus a negative 7x minus y plus 9 times j hat. Now that is equal to the gradient of some function little f and the gradient of little f is a vector with two components. One is the partial of little f with respect to x, and the other one is the partial of little f with respect to y. Now, these two vectors are equal if and only if their component functions are equal. So if this is my field and it has to equal the gradient of little f, then that tells me that the partial derivative of little f with respect to x has to be equal to that x component. And the y component here has to be equal to the y component there. So the partial derivative of little f with respect to y has to equal my y component. And we're trying to figure out what f is, because the fundamental theorem of line integrals says if I can find that potential function, I can evaluate it at the endpoint and the start point and subtract. I just need to find the potential function. And I don't know what it is, but I know it's partial derivative with respect to x and it's partial derivative with respect to y. If you want to find f when you know it's partial derivative with respect to x, you can undo that differentiation with partial anti-differentiation. So we know that f is the antiderivative with respect to x of the partial derivative of f with respect to x. We're undoing that and it would give us f back partially. And you'll see what I mean in just a second. So the partial derivative of f with respect to x is the x component of our field. So we'll write that down. And then we will anti-differentiate with respect to x, treating y as a constant. So we bring our 2 down, use the power rule here, add 1 to the exponent, divide by the new exponent. Now this is a constant with respect to x. The antiderivative of a constant with respect to x is that constant times x. 1 is a constant with respect to x as well. The antiderivative of 1 with respect to x is that 1 times the x. Now, typically at this point, I would add a constant of integration, but it has to be constant with respect to x. It's not necessarily constant with respect to y. So I might call that a g of y. The 2's will reduce, and I find that f of x and y is equal to x squared minus 7xy. Usually mathematicians like to write those variables in alphabetical order for some reason, plus x plus g of y. And if you're not sure about that g of y, remember what we're doing. We're undoing this differentiation, partial differentiation with respect to x. If I take the derivative of this with respect to x, I'll get 2x here. I'll get negative 7y here, plus 1. And the derivative of any function of y would be 0. So that's why it's constant with respect to x. We need a function of y here because that any function of y would be constant with respect to x and it would have a derivative of 0. So we know that f is equal to this. I just need to figure out what g of y is. If I want to find g of y, I can do basically the same thing, but with the partial derivative of f with respect to y. So f is the antiderivative of the partial derivative of f with respect to y, just undoing that operation. So we've got that there. And then I'm looking at this term by term. This negative 7x is constant with respect to y. The antiderivative of a constant with respect to a variable is that constant times the variable. Here I'll use the power rule. So we want to add 1 to the exponent, divide by the new exponent. And then the antiderivative of 9 with respect to y is 9y. And then we want to add a function that's constant with respect to y, but not necessarily with respect to x. So I'll call that h of x. And I'll simplify where I can. So I know f is equal to this. And if I take its derivative with respect to y, I get negative 7x minus y plus 9 plus the derivative of a function of x with respect to y, treating x as a constant would be 0. So both of these are f. I just want to find f in general though. Finding f in general requires that I find g of y and h of x. Since these two are the same function, I can match these in order to find g of y and h of x. So the first thing I'll do is I'll compare those in order to figure out what those are. And the first thing I will do is I'll look at these terms in this version of f and this version of f, and I will write down anything they have in common. So from this, I see that I've got a negative 7xy as part of my f of x and y, and I've got a negative 7xy from there. So that's covered. And then anything that they don't have in common, well, it has to be equal to a corresponding function on the other side. So here, I've got x squared plus x plus g of y. That has to be equal to negative y squared plus 9y plus h of x. So I've got x squared plus x here, plus g of y, and on this side I've got a function of y plus a function of x. This function of y over here, the negative 1/2 y squared plus 9y, that must be my g of y. And the function of x over here must be that x squared plus x over here. So we will just write down from here x squared plus x, and then from here negative y squared, or negative 1/2 y squared plus 9y. And we'd also add a constant of integration. So just to check to make sure that this is equal to both of these, let's make sure we have what we're supposed to have. F of x and y is supposed to be x squared, I've got that, minus 7xy, I've got that, plus x, plus a function of y, and that's a function of y, good. F of x and y is also supposed to be negative 7xy plus negative 1/2 y squared plus 9y plus a function of x, and the remaining terms include the x squared plus x plus c. That is a function of x. So that is our f of x and y. That is the potential function for our field. So if I want to evaluate the line integral of this conservative field over C3, according to the fundamental theorem of line integrals, all I have to do is find the potential function, evaluate it at the end point and the starting point, and subtract. Now let's look at our graph to find that ending point and starting point. Looks like we start here at x equals 0, y equals 1. And we end over here at x equals 2, y equals e squared. So those are our bounds in this version of, or this method of evaluating the line integral. So we're evaluating f of x and y at 2 and e squared and 0 and 1, and we're subtracting. Now f of x and y in our case is negative 7xy plus x squared plus x minus 1/2 y squared plus 9y plus c. But just like before, just like when you're using the fundamental theorem of calculus, you don't need the plus c, because when you have the c for the first one and the c for the second one, you're going to subtract them. They're going to be gone anyway. So we'll evaluate at 2 and e squared and 0 and 1 and subtract. So I've got negative 7 times my x value times my y value plus x squared plus x minus 1/2 y squared plus 9y. Replace all of your x's with 2's. Replace all of your y's with e squared. And then from there, we want to subtract negative 7 times x times y plus x squared plus x minus 1/2 of y squared plus 9 times y. But this time x is 0. Plugging in my x's, and then y is 1. Substituting my y's. And I get 0 here, and of course 0 here and here. This ends up being a negative 1/2 and a plus 9. This ends up being negative 14 e squared. Then I've got plus 4 plus 2. And this is minus 1/2 e squared squared. Multiply the exponents. That's e to the 4th plus 9 e squared. So it looks like I've got 9 e squared minus 14 e squared, which is negative 5 e squared. 4 plus 2 is 6, and we're subtracting 1/2 e to the 4th, and then we're subtracting a negative 1/2 plus 9 at this point. And so I have negative 5e squared minus 1/2 e to the 4th. It's from there and there. And then this is 8.5. I've got 6 minus 8.5. Or if you prefer, you could write this as a fraction. 9 is 18 over 2, minus 1 over 2 is 17 over 2. I've got 12 over 2 minus 17 over 2 is going to be negative 5 over 2. Or negative 2.5, which is the same result we would have obtained the other way. So that is our answer. That is the value of that line integral using the fundamental theorem of line integral.